In this video, we're going to talk about mass spectroscopy, which is kind of the tool that we use to help figure out the data that we used in our average atomic mass examples. This video is actually going to be done in a couple of parts. We're going to have the normal PowerPoint portion of the video. I'm also going to have a little bit of a demonstration where I'm going to use a tool that one of my professors made, a demonstration of how mass spectroscopy actually works. All right, so we'll start off with what mass spectroscopy is. The basic idea is that we can use this to find percent abundance. What happens is we take a sample of our substance. In this case, it'll be a pure element. We vaporize it and we ionize it. Ionizing means we remove electrons from it. It's then accelerated through a particle accelerator. Right? So we get these beams of particles traveling at very high speed. Now, if we do nothing to them, they're just going to keep traveling in a straight line until they hit something. One of the ways that we can affect this particle beam is by using a magnet. Like we talked about with J.J. Thomson's experiment, his cathode ray experiment, charged particles are bent by magnetic fields. Right? So if we turn on a magnetic field, we can cause these ionized or charged particles to bend. Based on the strength of the field, it will cause things to bend more and more. And the amount that something bends by depends on the strength of the magnet and how heavy it is. Right? Keep in mind inertia. The heavier an object is, the harder it is to get it to deviate off of its straight line path. So light objects will bend more than heavy objects. And what will happen is we ratchet up the magnetic field strength very slowly in a controlled manner, and the particles will start bending. And first, your light particles will bend at the exact right amount or curve around the tube and hit the detector. Then your heavier ones, and then your heavier ones as the magnet gets stronger and stronger. Right, so if we actually go to an example, just give me a moment or so to load it up. Okay, so what we have here is a simulation of mass spectroscopy. We have our mass spectroscopy device right here in the center, which is basically our bent tube, particle accelerator, magnetic field, and detector on the right. And what we're going to do is we're going to start off with fluorine. We're going to pass fluorine through. Now you see with the strength of the magnet as is, it's not deflecting the fluorine at all. So these little yellow beams right here are just kind of hitting the sidewall of the container. If I increase the magnet strength, you can see that yellow beams start bending more and more and more and more until it gets hit by the detector and it gets registered as a peak on our mass spectrum. There's only one peak here because fluorine only has one stable isotope. So with only one isotope, its abundance will be 100%. Now I'm going to change over to neon. We'll do the same thing, increase the magnet strength, and watch the beams as they start bending. And now what we get is we get first beam hit the detector, a little over 90% abundance. We increase the magnet strength, and now we have a second one hit. Now that second one is just barely a blip, right? So a very small percentage. And then as we keep increasing, we have a third particle hit at a little higher of a percentage, or about 8.8%. And if I keep increasing it, the beams just go completely off and no longer strike the detector. And then finally, we have sodium. So let's see what happens with sodium. All right, so we fire sodium. Hits 23, 100%, so only one isotope of sodium. This is how mass spectroscopy works. And what we'll pick up in a couple of seconds is how to deal with this resulting graph in our calculations. Okay, so now that we've had a chance to see how a mass spectroscopy actually works and the type of data that it will give us a graph, we'll actually use that graph to help determine the atomic mass of an element. What we have right here is this is the mass spectra of the element boron. We have two peaks on boron because there are two isotopes, an isotope with a mass of 10 and an isotope with a mass of 11. One thing to pay attention to in this is pay attention to the scaling of the graph. Sometimes it's scaled where everything adds up to 100. You can just take the number and work with it. In this case, though, the two bars don't add up to 100. They actually add up to a little bit over 100 because they got normalized. This isn't that much harder to work with. All we're going to do is the percent abundance is the fraction attributed to each bar based on the total. So what I'm going to do is, for example, for 10, for atomic mass 10, it goes up to about 25 or so. So we'll just call it 25. Mass 11 goes up to 100. The total is 125. The percent abundance of boron 10 is going to be 25 over 125. The percent abundance of boron 11 is going to be 100 over 125. So that's what we're going to take and plug into our atomic mass calculation, right? So atomic mass of 10 times the abundance, which is 25 over 125. And then we're going to have atomic mass 11 times the abundance, which is 100 over 125. Add up these two results, and we wind up with 10.8, which is our average atomic mass for boron. And this, again, does track with what you see on the periodic table. Right, so this is mass spectroscopy. I will have you guys working with this data a little bit. So we will see you guys in class to practice.